Morning, evening, and afternoon to everyone wherever you are, and welcome to Note to Noise. And I'm Vivek RAMAMOORTHY. I'm the ESR3 of Note to Noise project. I have a mechanical engineering background from the Indian Institute of Technology Madras, and I have switched my fields to computer science. And I work with Ender and Andrew from the University of Nottingham as part of the computational optimization and learning lab. And I also work with Luke and Francois Xavier from Metalist Research Lab. So Note to Noise, the EU project, allows me to work with both the academia and industry. And Ender, Andrew, Luke, and FX are my supervisors. And with the expertise of Ender and Andrew in computer science and Luke and FX in porous materials, my work is on the optimization of acoustic porous materials. And mainly I focus on heuristic and metaheuristic techniques. And without further ado, I'll move to my presentation. And well, we all have traveled in aircrafts for our vacations and our business trips. What we would have observed is the comfort levels, the noise levels inside the aircraft would be typically high, that we wouldn't be able to talk to the next person without raising our voices a little bit, or we wouldn't be able to watch movies as comfortably as we would be able to at our homes or in movie cinemas. So the reason being the external noise from the engine and the passage of air over the surfaces of the aircraft produce noise, and that noise is prevented from entering the passenger cabin from through sound absorbing porous materials placed on the walls of the fuselage. And these materials constitute a significant amount of dead weight, and the question is, can we optimize them? And of course we should. And is it ideal to completely fill the available space with these porous materials, or is there a better solution? It turns out that there are better solutions. By creating cavities of air pockets within the poroelastic materials, we can create resonances within them and allow for more sound absorption. And with this as the motivation, okay, so we have further reasons to care about optimizing sound absorbing materials, not just aircraft. So we can, since ACAR, the Advisory Council for Aviation Research in Europe, predicts that in 2050, 70% of the metals in automobile industry and the aircraft industry will be replaced by composites. We will need to worry about the increase in noise levels due to the light weight of these composite materials, which are not good at sound isolation. And so by adding porous materials, we can bring down the noise levels, but by adding these materials, we again, negate the lightweighting benefits. So we need to optimize these porous materials in order to retain the benefits of using composites and achieve a target of reducing 70% of the weight of the current automobile and aircraft structures. And to do that, we need technologies, and I'll be looking into one such technology. And we also have other applications such as building and sound barriers across the roadways. So we need these to prevent noise pollution, which affects a huge number of people, and it also contributes to increased risk of heart diseases through improper sleep. And we would need to improve the conditions of such buildings, and we would need to simultaneously reduce the cost of such porous material usage when considering noise in buildings. And the other thing is in space applications, to prevent the payload from experiencing uh, very high levels of noise and vibration, there are porous packaging materials placed surrounding the payloads, and these contribute to a significant amount of dead weight as well. And by optimizing them, by getting every gram out of the porous materials we can think about exploring, in the future, in late future, exploring further stars and exoplanets, and that probably is the purpose of humanity, as far as I think, and we have good reasons, uh, 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 as we can see, to worry about optimizing sound absorbing materials. Now, the main aim of my research is to investigate novel and existing optimization approaches in designing acoustic porous materials. Now, this not only pertains to optimizing the typical multi-layered sound packages. It is also I also look into optimizing the shape and topology of these structures. And by shape and topology, I'll explain in a minute. And today's presentation will be focused on shape and topology optimization. And let's start with a test problem. So consider we have an impedance tube, and we have a region, let's call it design domain, in front of the rigid wall here, and we have an acoustic input. Our goal is to absorb as much as the acoustic energy that is coming from the acoustic source, and to do that we are given a block of porous material, and we need to we are allowed to cut or carve this material into any shape or any topology, meaning a number of holes, and the question is, what is the best shape that we can obtain that maximizes the absorption? And we know that wedge shapes are good, but are there better shapes? It turns out that in some cases wedge shapes are not the best, and it is fairly obvious. And the question is to answer what is the best shape, and to answer such questions, to provide solutions, to try to provide solutions to the absolute best topology and shape possible, we look towards technologies such as topology optimization. And topology optimization is the concept of optimizing both the shape and the topology simultaneously using algorithms designed for it, such as the one I will show you in this video. So we have a toy app created by the TU Denmark Topology Optimization Lab, and here I demonstrate in real time. This is real time. I am not sped up. So by adding loads resembling that of a bridge and optimizing in real time the best shape of solid structures that carries the loads given these boundary conditions, we find out that it readily gives us the well-known suspension bridge solution. And this is the kind of technology that structural topology optimization gives us, and this can be used in acoustics as well. The usual algorithms used in topology optimization are the solid isotropic material with penalization method, which is the most common method, and which is also what I showed a while ago. And this method can be implemented in less than 100 lines of MATLAB code, as demonstrated by Ole Sigmund. And Ming Zhu yesterday mentioned this and further articles to look into for beginners. And also we have all the major FE commercial software players developing tools for performing topology optimization. And we have seen a presentation from Tom and Ming yesterday as well from Altair. And I'm also aware ANSYS and Abacus are providing such tools. And most of these tools use one of these methods. So the SIMP method is something which is which uses the gradient of the objective function with respect to the design variables and moves in the direction of better solutions incrementally. And the way the algorithm does is it can be controlled by the parameters involved in the algorithm. And Beso is a very intuitive design heuristic that has been used since ages by engineers. So if an element, if a structural element, if a region in a structural element has high stress, we add reinforcement around that region. That is, we add material to that region. And if a region is not stressed as much, we remove materials from that region, and that is Beso. It's not an evolutionary algorithm in the context of computer science, but it is just a constructive approach with such a name. And the bidirectional means we also add and remove materials, alternatively during the algorithm. The level set method, as Ming covered already yesterday, it is a very fairly recent, relatively recent method, but it's quite old too. It's 2 decades old now, and it uses a higher dimensional surface and uses the level set, that is the constant level of that higher dimensional surface, as the boundaries of the topology. And I have an example from Diljan and all others, which is a recent paper published on transmission loss problems in impedance tubes. And these are some of the best shapes that they have obtained. And this is the kind of method that level set is. And the goal is to optimize the surface to optimize the topology. And if you look at compliance minimization is the standard problem domain, which I showed in the video from TU Denmark. And acoustic optimization has been catching up. And as far as I can tell, there are 30 to 40 papers already published which use topology optimization in acoustic domains, different domains, right from horns, room ceilings, the optimal shapes of the foams that you can place on the ceilings of the room, of a room to optimize the sound performance of that room, and car cavities, mufflers, scatterers, and sound barriers, and many others, including impedance tubes, the standard impedance tubes. And we can observe that SIMP method is being used in most of the cases, and Beso and level set being used in some of the cases. Although there are some use of metaheuristics, I have not showed here. I've just shown some representative examples, and there are probably a few examples of metaheuristics used in acoustic topology optimization as of now. And there is a gap in knowledge because SIMP, Beso, and level set are not. So this problem is a discrete optimization problem, and there are much more established standard algorithms for discrete optimization, and SIMP, Beso, and level set are not the standard ones, and they are domain specific ones which are good at solving this particular problem. And the gap in the current knowledge is to see how metaheuristics can play a role in assisting, aiding, or substituting the existing methods on some kind of problems which the conventional methods cannot deal with. And let's look at some of the shapes produced by some of the researchers in acoustics using topology optimization. And in here we have Lee and others who published who optimized wedge shapes, anechoic wedges, anechoic chamber forms shapes to improve the sound absorption performance in low frequencies, and they have a better solution than the typical wedge shape here. And During and others, and in this publication, Ole Sigmund also is an author, and they published room ceiling foam placement optimization, and this is the kind of solution that they get. And here we have Cook and others optimizing the placement of sound absorbing panels in the car cavity, in the surface of the car cavity really. And here we have microstructure optimization, and we have sound barrier optimization. This is a BEM example, boundary element method example. And in this, they optimize the placement of rigid or porous material in the lining of a sound barrier to improve the absorption performance in a given setting. And we also have many applications of mufflers, and I provide one example wherein rigid and porous materials are simultaneously used to fill exactly this particular part in a muffler and find the optimal shapes at different frequency ranges and so on. So with this is not new. This is being the interest in topology optimization in acoustics is catching up, and soon we might see more papers in this field, but there is still a lot of gap which needs to be uncovered, gap in knowledge. And my contribution will be in terms of metaheuristics. Okay, let's look at the problem. How do we optimize the shape? So typically the problem formulation when using finite element works like this. We discretize the design domain and the other parts, and within the design domain we assign an interpolation variable which is chi here, and which is a vector, and it determines the decision as to whether or not porous material is placed in an element, in a finite element, or air is placed in a finite element. And the optimal assignments to chi is the solution we want. And so we chi such that alpha bar, the sound absorption coefficient averaged over range of frequencies in some way, needs to be maximized. And this is the problem we are dealing with. This is clearly a discrete optimization problem. We have decision variables chi, which can take a discrete set of values 0 or 1. If so discrete problems are generally hard to solve, and SIMP and other methods, SIMP method particularly is not a discrete method, it is a continuous method. And the way SIMP solves the problem is to use an interpolation scheme. So you allow materials between air and porous material to be placed in the design domain, so that your chi value can take values between 0 and 1, and to assign properties to each of these intermediate materials, what you do is you use some kind of an interpolation equation to get the properties for each element. So if chi is 0, you will get the properties of air. If chi is 1, you will get the properties of porous material. And this chi to the power p, you could do a linear interpolation, but this chi to the power p is traditionally a concept used in structural topology of compliance minimization problems, and we adopt that. and there are reasons. There are other interpolation schemes we could opt for. There are papers solely dealing with interpolation schemes, and this is the standard one which SIMP uses. And a little more details about the problem. So to calculate absorption for a computer science audience in the computer science researchers in the audience, it uses it solves a system of linear equations. So it's expensive. So the function evaluation takes most of the computational time compared to other aspects of the algorithm. And the search space size for the decision problem I discussed before is 2 to the 2 power n, which comes from the fact that there are n elements in the design domain. Assuming there are n elements, we have 2 decisions for each of these elements, whether you place air or whether you place porous material. So that turns out to be 2 power n, the search space, and not necessarily because of the search space, but mainly because of the expensive nature of the objective function evaluation. Exact procedures become very expensive, and one such noteworthy paper is the paper on COC algorithm by Zhu and Roswani. We met Zhu yesterday, and he's one of the pioneers in this field. And Stolp and Benzo tried to find the exact solutions to the Zhu and Roswani problem. And that's one of the benchmarks. So they used branch and bound or other pruning techniques to find the exact optimal solutions. And that's one of the benchmarks still today that one can look at when thinking about using exact procedures to solve the problem. To be clear, what I mean by exact methods is they guarantee you that the produced final optimal shape is the global optimal shape. And heuristic methods are those that do not guarantee, but essentially give good enough solutions, very good solutions in quick time. So the other thing is, to use SIMP-like algorithms, we need the gradient, and it turns out that it is possible to calculate the gradient. It is not always the case, but Lee and others in 2008 demonstrated this in their unified modeling approach paper, which we also saw a bit earlier. And so to calculate gradients, we can do that fast for this domain. And to do that, we use some adjoint technique and back propagating the derivatives up to the material properties, and from there we can compute the sensitivity. In this case, it takes 3 times as much time to compute the derivatives, the gradient, as it does to compute the sound absorption. So I'm not going to go into the details of the finite element procedure to solve. Abhilash, the ESR1, helped me implement these finite element techniques, and the idea is this. So we feed in the decision variables, whether or not porous material or air is present in a particular element, or whether or not it is a material between porous material and air. We feed that information to the finite element solver, and it uses the properties. It interpolates and uses those properties for each element, and then finds the absorption curve for those for that structure, acoustic structure. And to do that, we use equations, the mixed formulations by Atala and others, and Beko and Johan. And we also use the sensitivity equations from Lee and others. And to use an algorithm to perform topology optimization is just wrapping around this solver. And what we do is we take the objective function value, the absorption values, and feed back to the topology optimization algorithm to determine what the next new topology is going to be. And we iteratively do this to find the best found shape, the optimal shape from that algorithm. And in this presentation, I will discuss the some metaheuristics, some popular metaheuristics, and existing and somewhat standard heuristics such as hill climbing and constructive heuristics applied to 7 benchmark problems in acoustic topology optimization using porous materials, all of which are in impedance tube, which vary in dimensions and mesh size and materials used, etc. And so we have 2 algorithms which use the gradients. So we restrict the amount of function evaluations. Function evaluation meaning absorption computations. So we restrict the number of absorption computations, finite element solution, number of times the finite element solver is invoked. We limit it to this number, 4096 and 1366. And also some of these algorithms, I'm not going to go into the details, but they start from different starting solutions, and so they can end up in different final solutions. So we wanted to see how the performance is on average given the stochastic nature of the algorithms. So we ran those algorithms 31 times and found what the solution was in each trial. And we will look at the results shortly. So this is an illustration. When we run 31 trials, after each function evaluation, the algorithm may or may not find a better solution than what was found thus far. And when we plot the best found solution thus far for all the 31 trials, we get this sort of a graph. We remember we are maximizing sound absorption, so we want the curve to go up. And what we do is, in order to compare different algorithms, we average this at every function evaluation step and get a single line. In the one in orange, the CMA trial average line, is what we will use to compare. But keep in mind that we are performing 4096 absorption computations. We are invoking the solver 4096 times, and we are doing this 31 times on top of it, and to get this single line. And we get this line, and some of the algorithms I discussed earlier are continuous algorithms, meaning they allow intermediate materials. Some others do not allow intermediate materials. They are discrete algorithms, combinatorial optimization strategies. And to be able to compare these 2 strategies, we need to work in the same search space. It wouldn't be fair to compare continuous solutions with discrete solutions. So what we do is, ultimately, we want the solutions to be either air or porous material in each element. So we do a simple rounding to discretize these solutions in the end of these continuous algorithms. There are variants of these continuous algorithms as well, which discretize at every function evaluation step before computing the sound absorption. So they need to be considered as discrete algorithms, because what we subject to in the objective function is a discrete solution in the end, whereas the algorithm is looking through the continuous search space. So essentially they are discrete algorithms, and that's why we have the discrete solver and discrete search space here. And we have popular metaheuristics such as genetic algorithm, taboo search, covariance matrix adaptation, evolution strategy, and differential evolution. And coming back to the heuristics, we have hill climbing, which is if you flip each element between air or porous material, and then if it is improving, you accept it, and then move to the next element. And if you keep doing it, that's hill climbing. And in constructive heuristic 1, we keep adding material to the element where the increase in absorption is the maximum. And in material removal constructive heuristic, we start from a fully filled solution, fully porous material filled solution, and remove porous material from the places where the reduction in absorption is the least. Sometimes they can lead to increase in absorptions, but the algorithm works like this: least decrease in absorption is the move operation that the algorithm will make. So it's fairly simple to understand, and I'm not going to go into the details of these algorithms. And we have SIMP, two variants of SIMP without a density filter, just to compare, because we don't use a filtering technique. We are going to ignore manufacturability restrictions, and we are going to consider that these manufacturability restrictions are going to be applied in the post-processing stage. And what we care about now is what we are looking at is the raw performance of these algorithms. So we trial average and we discretize, and then we have this result. What we have here is all the algorithms on a runtime plotted against, so the value of absorption average plotted against the runtime. So after a certain amount of time in a reference machine, the algorithm reaches an average of that level of absorption is what this plot is. And we see that SIMP algorithms are initially very quick to reach a good solution, good quality solution, and then after the end, the solutions are rounded, and because of rounding, there is a reduction in absorption. Whereas other algorithms such as hill climbing and taboo search, even though they are initially slow, they reach a good solution towards the end. Whereas in some other problem instances, remember that I told you we do such such studies for 7 different problem instances. Problem instance being one example of a problem, and in a different problem, the behavior is different. In this problem, SIMP algorithms outperform all other algorithms and find close to the best solution found. However, hill climbing slightly finds better solutions in terms of absorption. Very small improvement in absorption, but nevertheless, hill climbing finds such solutions, and so does CH1. And we don't see it clearly here because the lines overlap. So we look at the so we got the results, but remember that this point is the average of 31 points. So we will look at all the 31 points distributed in a box plot, in a distribution plot, wherein the lower end of the box represents the 25th percentile and the higher end of the box represents 75th percentile, and the lines represent the span of the solutions, and the crosses indicate the outliers. So so the higher the solutions, the better the algorithm is, and we have ranked the algorithm based on the median performance. And we see that hill climbing, CMAD, in this order, we have the ranks of the algorithms for problem instance 1, whereas for problem instance 6, we have this order where SIMP with density filter performs much better than in this problem instance. So this is the kind of result we have. This shows that for the given budget, some metaheuristics and heuristics can outperform the conventional SIMP method. And however, when we look at low function evaluation budgets, SIMP still is the best algorithm out there. And when we look at all 7 problem instances, we can rank them based on a threshold ranking, and based on the median performance, and then we see that hill climbing finds the top solutions in 6 of the 7 problem instances, and it is not able to find the top solutions in one problem instance, the problem instance 3. Whereas SIMP and SIMP F2, even though they perform well on some problem instances, problem instance 6 and problem instance 4, on other problem instances, their performance ranks well below the other algorithms, mainly because of the rounding effect. And that's indeed why yesterday the FX asked a question to Mingzhu regarding this, if you remember. And so some of the findings are that greedy hill climbing performs well in most cases. And we also observe that no algorithm clearly outperforms all other algorithms in all the problem instances. So hill climbing doesn't perform well in one problem instance. So there is no algorithm which can be, considered clearly suitable for this problem domain. And this is the result of a systematic study, and also the Wilcoxon correlation tests also indicate that the p-values are sufficiently higher to reject the null hypothesis in all of these ranking cases. And we will not go into the details of that, but for more information on the results, one may refer to this paper, which is recently accepted and will be published soon. And we also look at we also look at the volume fraction of the kind of solutions that these algorithms produce and the absorption. So ideally, we didn't consider a volume fraction constraint in this study because some algorithms cannot allow for volume fraction constraint very easily, and we are not looking for that solution because remember the problem is we have a full block and we want to remove materials and find the best solution. And considering that, we see that different algorithms find solutions in different regions of the search space. The reason I say different regions is for a given volume fraction, there is a region within the search space which we can explore, and that's what SIMP does traditionally. So SIMP is supposed to do traditionally. And whereas in this problem instance, we clearly see the distinction. So GA identifies solutions in this region, and CMAD identifies solutions in this region. And hill climbing, we see that it clearly produces solutions in terms of the raw value of absorption. It produces slightly better solutions than all other algorithms, although they have the solutions that they produce, all the 31 solutions, they have a very high volume fraction. That is, most of the design domain is filled with porous material. So these are the kind of solutions that these are the best out of all the trials of all the algorithms that we discussed. These are the solutions for problem instance 6. Again, we have such shapes for other problems, but we will only look at problem instance 6, and we see that SIMP almost fills the full grid with a very thin layer left with air near the rigid wall, and SIMP without filter tries to do something similar, but it is not able to put a clear layer because of the lack of filtering. And CH does the same. It puts a layer next to the rigid wall, and these arrows indicate acoustic input. And it seems that in this region, we need to remove material to improve the performance of the sound absorbing layer. So we see that being reflected in taboo searches results as well. And CMA, CMAD, DED try to find solutions, even genetic algorithms. These are popular algorithms which are designed for black box optimization, but for this given budget, they did not reach a clear, smooth bounded solution. So we see that CMA and all these algorithms try to remove materials from here, but That's all we get from this analysis. But in future studies, we can look into implementing filters along with these algorithms, which may improve the performance significantly. We wouldn't know, but this is a preliminary result that we obtained to check the initial performance of these algorithms. I'm about to conclude in a couple of slides, and we have we obtained very different results in each trial from all the algorithms, in fact, and we can see the kind of shapes produced by each algorithm is a unique variety. And we see taboo search with unique kind of solutions. We see simp F0 with such kind of solutions which try to put a layer and get lost. We start simp from different initial conditions. And when we use a density filter, it clears out that this path, this chaotic layer. And we see in most cases, even with density filter, we obtain different results starting from different starting points. And we see constructive heuristics were deterministic, so we have only one result. And what's on top of all these shapes, the absorption value averaged over a range of frequencies. And they are supposed to be as close to 1 as possible. Okay, so we have looked at some of the findings, and we will look at some of the we will look at some reasons why as to some methods don't seem to be performing well. If you look at, so this is a discrete problem, and we have compared the solutions as a discrete problem, and we observe that the continuous approaches CMA and DE and SIMP, they were not able to produce 0, 1 shapes by default. They did produce other shapes, and when rounded, they led to solutions which had a reduction in the absorption value. That's not ideal, but also CMAS and DE are designed to work with less number of design variables, and they are designed to search within these within the bounds. So if chi can take values between 0 and 1, CMA and DE are searching solutions between 0 and 1, whereas what we are looking for, what we desire, is solutions which are in the corner. We want solutions which have air or porous materials only in each element in the design domain. So that's one of the reasons why CMA and DE, the continuous algorithms, did not outperform others, did not perform as well as others. And do we know the exact solutions of all these problem instances? No. The reason being there isn't any research paper which details a branch and bound method for this problem domain. And brute force, even for very small problem instances, can take very long times. If the design domain had 30 elements, we calculated that it would take 12 days on a reference machine. If it had 35 elements, it would take 1 year to compute all possible solutions and find the best solution. And if it is 70, it would take close to 14 billion years, which is about the age of the universe. So it's clearly not possible to brute force. So we don't know the best solutions for these problem instances. Whatever we know are thus far the best found. And is the problem NP hard is a question. So since Andrew discussed it yesterday, I throw some light on it. We can draw parallels between the topology optimization problem and the knapsack problem. So instead of an arbitrary a function like this, which uses system of linear equations, solves system of linear equations and solve, if we have summation values and x's, so knapsack problem is a problem where you have to fill the knapsack with the available valuable items, and you want to maximize the value of the knapsack, value of the items in the knapsack, and the problem is to determine whether or not you pick each item or not. So this is similar to whether or not you fill air or porous material in each element in the design domain. So there are some similarities. even though the knapsack problem has the objective function, a linear objective function, knapsack problem is NP hard, and we know if in topology optimization it can be very nonlinear depending on the material definition and the interpolation scheme definition. So still we cannot, there is no proof yet, but it's likely NP hard, it seems, but we cannot say anything for sure at the moment. And I listed out all the findings which have been already discussed, and I'm just listing them out here. And the future prospects of this study would be to explore gradient-based metaheuristics. There is a class of gradient-based metaheuristics. An example is stochastic gradient descent, and we need to look at ways to use the gradient. When gradient is available, why shouldn't we use it? So that's one of the things that we need to look into. And multi-objective optimization. In this study, we didn't reduce the volume fraction, so we received solutions across the different volume fractions. Make the volume fraction an objective, reducing the volume fraction an objective, and it will become a multi-objective, bi-objective optimization problem. The other thing to look into is hybrid approaches, which combine the metaheuristic techniques and the simple like standard algorithms, which can find quick improvements to a given solution. So there is a lot of scope in this domain, and we look forward to exploring it further. And with that, I conclude my talk. Thanks for the opportunity, and